I was fed up with commercially available tool setters that were not splash-proof and glide so poorly that they sometimes even get stuck. So I decided to design and build my own with a linear ball bearing guided probe head, replaceable stainless steel touch surface, and a micro-precision photoelectric sensor. In this video, I share with you how it is made. Hello and welcome to my channel. First of all, please excuse my raspy voice in this video, but I've catched a cold and I don't want to let the AI talk for me yet. I've bought these two tool setters in the past and they are both junk. This one has an aluminum body and a steel probe head which goes over the main body, which is good because the sliding elements are protected from coolant splashes this way. The head glides with a slotted steel shaft in the body and its top limit is set by a grub screw. But the spring force is so low and the tolerance is so poor that sometimes the head gets stuck, as you can see here. An absolutely useless piece of crap for, believe it or not, 250 euros. The other one is just half the price and has a stainless steel body. The touch plate, which is stainless as well, is in fact the shaft that glides in a plastic bushing. The spring force and tolerances on this one are much better, but it is not splash proof. I managed to get drops of coolant in the small gap between the shaft and the housing, causing it to bind as well over time. Another issue that both have is that the touch surface is not replaceable. So when you manage to slam an end mill with G0 into the tool setter, it leaves a nasty mark and the entire tool setter is garbage. Both work with inductive proximity switches, which I also don't really like. One sticks out like a Thor's thumb and the other one is so tiny that I managed to get a loose connection on the cable over time. So when I built my mineral cast router, I already decided to make my own tool setter which addresses all these issues. It proved to work quite well and therefore when I finished my new woodworking router, it was clear that I make one again. This time, however, I made it a little bit more simple without an integrated air blast cleaning nozzle. I'll show you later why. But first, let's dive into the cut model to have a look at the design. The tool setter is made out of 21 parts in total, 5 of them to be made by myself. The sensor base, the bearing housing, the touch head and touch plate, and the sliding shaft. I also added a small magnet to the bottom and a miniature cable gland to protect the sensor. The touch plate is made out of stainless steel and is replaceable in case of damage. The key elements are the micro photoelectric sensor and the linear bearing, but the main part which determines the size is in fact the spring. I wanted to have a mild preload between 3 and 4 Newton, which would not exceed 10 Newton during the actual measurement. With this, I always have a very precise position of the probe head during the entire travel and still no risk to damage even the tiniest end mills with less than 1 mm in dia or sharp-pointed engraving end mills. With the selected spring, I ended up with 3.6 Newton preload and 7.2 Newton at the point of measurement, which is roughly 3 mm into the travel. The total travel, however, is 10 mm, so if you want, you can hit the probe with high feeds and then slowly reverse for measurement. The shaft is made out of precision ground steel rod with a 6 mm dia and H6 tolerance, which fits nicely into the LMU6 linear bearing. This gives a very smooth, uniform slide without any wiggling whatsoever. The shaft slides into the fork-shaped sensor and interrupts the light beam. Quite simple, isn't it? So, let's have a look at the machining of the parts. Since most of the parts are round, my first instinct was to turn them on the lathe. So I started by turning the stock to the biggest outer diameter first. This is 6082 aluminum, by the way, because I wanted to have the possibility to anodize the parts later on. After this, I cut the stock to pieces on my bandsaw and turned it again on the lathe to a defined length. But as you may have seen, this time I've made not only one, but a small batch of 12 tool setters. And since this is a manual lathe, and to be honest, I'm not much of a lathe guy anyway, I finally decided to mill the parts instead. So in order to properly hold the round stock in a vise, I machined soft jaws first. And after this, the milling could begin. The final operation is to tap the M3 threads, and yes, I do this with a cordless drill. I have had some issues with this in the past, but ever since I use this cutting paste, I have never a broken tap again, and I'm confident enough now to even tap delicate threads like M3. I have linked it in the description below. And with this, the first part is done and I can move on to the next part.
Since I do not have a force axis yet, the next op was a little bit cumbersome. I had to machine the 2.5mm holes for the M3 grub screws that hold the replaceable touch plate in place one by one. I eyeballed the 120-degree spacing and this was close enough. Then it was time to do some power tapping again, and I noticed immediately that 7075 is much tougher than 6082. Even with the tiny M3 threads, it was difficult to hold the part, so I was extra careful. The last part to be done on the mill was the sensor bases. This is a straightforward part out of the regular 6082 bar stock.
And finally, some drilling and manual tapping again.
The remaining two parts are made on the manual lathe. First was the sliding shaft. This is made out of precision ground steel rod, but it is not hardened, which makes it ideal for turning. It is 6 mm in diameter and has an M5 thread on the top. A few years ago, I made a little helper to machine threads manually without the need to mess around with gears and feeds. I saw this on Joe Pieczynski's channel, and this is such a useful resource that I highly recommend you to check it out. I have a link to his channel in the description below. The rest is straightforward turning. A small groove for a retaining clip and parting to rough length. With such a small diameter material, I always try to work as close to the chuck as possible, so I have to reposition the stock a few times. In order to get a precise length on the second side, I add a retaining washer first. This gives me a defined position in the chuck and I can finish the shaft. The last part to be made before the assembly is the touch plate. This is made out of stainless steel. I first turn it to the final outer diameter. Then I face the top, cut it with the bandsaw, and face the second side to length. I use a pair of parallels here to always have the same offset in the chuck. With those 5 parts made, it was time for the assembly. At first I pressed the linear bearing into the housing. Then I insert the shaft and screw the probe head on with the spring in between. Next, the touch plate is fixed in place with 3 grub screws. The next sub-assembly is the sensor base. I first glue in a 5 mm plexiglass rod, which I cut and polished off camera. This transfers the light from the sensor LED to the front of the base. Then I add a magnet to the bottom, which helps to secure the tool setter on a dedicated plate. After this, I fix the sensor in place and add a cable gland. The sensor is a Panasonic PM25C3, by the way. And finally, the two sub-assemblies are screwed together with an O-ring in between for additional splash protection. And this is what the final tool setter looks like. Quite nice, isn't it? Please be so kind and leave a comment below what you think about it. The last thing to do was of course to install and to test it. I still need to make a small steel plate or an aluminum one with a magnet to locate the tool setter in place, but for the test it works as well like this. My probing routine advances the tool with G0 roughly 10 mm above the tool setter. Then an airburst from the Z-axis cleans the touch plate from chips. Next the tool goes down with 200 mm per minute onto the tool setter until it triggers. Then the axis is reversed and the tool moves up with 20 mm away from the setter. When the sensor untriggers, the tool length measurement is taken and the axis moves rapidly to G0. I finally tested the repeatability of the tool setter by jogging the tool on the setter and to reverse it until the sensor triggers again. I did this 5 times and the trigger point was always identical within a few microns. That's good enough for me. I've made a small limited edition batch of 12 tool setters in total. They are available in NPN or PNP. When you're interested, please send me a DM. Thanks for watching. If you like this video, give it a thumbs up, subscribe to the channel and hit the notification bell so you don't miss the next videos. Stay tuned and see you next.